Okay, so this is the third example, and again, the first part A is the maximum shear stress, which is what we discussed on Friday. B and C have to do with rotation, which we're going to cover on Monday, but I'm going to go ahead and do the whole problem so I don't have to repost a video. So we have a compound shaft drive, several pulleys. We have segments 1, 2, 3, and 4. Segments 1 and 2 are made of hollow aluminum with an outside diameter and a thickness. Segments 3 and 4 are solid, and they have a 1.5 inch diameter. They gave us the shear modulus, and we want to determine what is the maximum shear stress. So in order to figure out what is the maximum shear stress, we're going to have to find internal torque, internal torque, internal torque, and here we have two different segments, and so then shear stress is T rho over J. So we have the same row, different row, so they have the same torque but different rows, and then different J's. Oh, and you can even see where I'm pointing it because I printed this so ginormous. Okay, so we have to find the internal torque at each section, because if I want to know the shear stress is T maximum C over J. Okay, so I have to find that internal torque for each of these, and then I can go back and take their cross-sectional properties to calculate the shear stress for each of these, each section, and then I can then determine which one has the maximum. So material properties, if we are looking over here at 3 and 4, okay, we have steel. So I'm going to call that from E to D, and from D to C, we have steel. And we were given a shear modulus of 12,000 KSI, and I don't know what I need to do with that unit yet, if I need to make it a pound or keep it as kip. It is a compound wall thickness solid. So if it's solid, then the diameter that I'm given is 1.5 inches, and that tells me that the radius is 0.75 inches. Okay, that's equal to my C. J is going to be pi over 2. C to the fourth is pi over 2.75, okay, to the fourth. And that's what I have on this. So now we can come over here and look at C to B and B to A. C to B, B to A. And this is made out of aluminum, and it is hollow. So that means we're going to have an outer diameter and an inner diameter. And we have an outside diameter of 3, so diameter outer is 3. Therefore, our radius outer is 1.5 inches. And it has a wall thickness of 0.125 inches. And because I'm dealing with radius, because of my equations that I use, I can take the radius outer minus thickness, and that'll give me my radius inner. So I have radius inner equals 1.5 minus 0.125 inches, and I get that radius inner is 1.375. So my J is going to be pi over 2 radius outer, 1.5 to the fourth, minus radius inner. Okay, and I like to just have all of this stuff set up so that, again, I don't have to think back. I don't have to try to find numbers. I have everything listed that I know. So now I've got to find internal torques. That means I have to cut and find my post-it note, because you all know I love my post-it notes. And if I'm coming from the left to the right and I cut right here, I have this little tiny segment, and I'm twisting back at 95 pound-feet, and I'm going to assume internal positive, so that's twisting towards me. Okay, and so now if I do the sum of my torques equals 0, I've got positive torque E to D. That's minus by right hand rule coming from right to left minus 95 pound-feet equals 0. So my torque from E to D equals 95 pound-feet. Okay? Positive. You could also look at it like this. This is positive is thumb right here. I'm circling back so I can show it out. Internal, positive, and I could sum my torques that way. So now when I sum torques, to the right is positive, I have a positive and then a negative. So even though it's positive by sign convention, when I sum torques, it's negative. It's just like when we had internal shear. This is positive sign convention. Going down is positive, that internal shear. But when I sum my forces in the y direction, it is a negative shear because it's going down according to the sign convention for equilibrium. Okay? So now I'm going to move this over. 3 and 2, even though they're different materials, different cross sections, etc., they're going to have that same internal torque. So we're going to draw across this way, and I've got 95 going back. I've got 270 coming forwards, and I'm going to assume positive internal behavior, right-hand rule, positive coming towards me. So that's my torque from D to B. So now if I sum my torques, okay, they have to equal 0. Okay, I have a torque from D to B. I have plus 270 minus 95. So again, I'm using going from the right to the left, and I'm doing all of my torques. Positive dB, positive 270. Oh, that's a minus 95. So when I set this up, I'm going to have dB equals negative 270 plus 95. And I can find then that my internal torque there is negative 175. Okay? Again, we could look at it like if I'm looking going this way, this would be that, this would be, and I'm assuming this way, coming from left to right, positive, negative, and that's coming back. I'm assuming it positive, and when I set these up, I'm going to find that truly has to be in this direction. So I have 95 that way, 175 that way, 270, it's all in equilibrium. There's like multiple ways to look at this. You just need to find the way that for you is consistent and keep up with that. Now I could go all the way across and draw this big thing, but because it's free to rotate on both sides, I can come back over here, and I have 650. Okay, if I'm looking at internal positive, thumb away from the cross section, from away, circling to the back, that's my torque from B to A. And if I sum my torques, they have to equal 0. I'm going to start here, so I have a positive TBA. Okay, positive TBA. Negative 650, because I have to keep my sign convention the same all the way from left to right when I'm doing equilibrium. So positive TBA, negative 650, minus 650 equals 0. So TBA equals 650. Now, I can look at that and that makes sense. Twist, twist. I have to twist opposite and opposite directions to keep it from moving. So you can, you can visually look at that's correct. So I have from E to D, I have a torque of 95 pound-feet. From D to B, I have a torque of negative 175 pound-feet. And from B to A, I have a torque of 650 pound-feet. This is like the wedding cake problems. If you are struggling at all with this, you've got to get some help. Okay, you've just got to get help. You have to know how to cut these things correctly and find internal. You cannot just look at the outside and just grab numbers. It's just like the wedding cake. Remember the wedding cake? If I have a force and I have a force and I cut here, I have to look at the whole thing and I have to sum my forces in the y direction and, whoops, focus, and I'm going to have a negative, plus, and then I assume this in tension, negative, and the math will tell me whether this internal is tension or compression. Okay, so now that I have this, I'm going to draw myself a, I'm kind of like fold it like this. Let's see if we can do this. We're going to draw ourselves a torque diagram. So if I'm looking at my system and I come down, this is just like a shear and moment diagram. Okay, when I look at my torques, so these are my torques, I have a positive 650. I have a negative 175. And I had a positive 95. So I now can just look at this, pound-feet, and I don't have to go back and find my numbers. And I'll be able to sketch then. I can sketch, after I do this, a shear stress. And then I'll be able to sketch an angle of twist. So it's just like shear and moment diagrams. We're just moving down the line. Okay, so I need to determine the maximum shear stress. So that means that for each section, I need to calculate T rho over J. So I have my T's set up. Here's from A to B to C to D to E. I have torques. I have rho. That is for maximum. It's going to be that outer diameter. And I have my J equations. So let's go set it up. From A to B. Shear stress from A to B is the torque from A to B. It is my radius from A to B, and it is my J from A to B. I have 95 pound-feet. I have a radius, if I go back and look at my sheet, of 0.75 inches, and I have a J of pi over 2, 0.75 inches to the fourth. You guys see a problem with this? I'm usually going to be given torques in pound-feet. 12 inches per foot. So I have 95, 0.75 times, 12 times to convert it, pi over 2, 0.75 to the fourth times, divided by. I get a shear stress of 1720 pound inch squared. So I could go back over here now. So this is a pound per inch squared. And I could say, okay, I have 1720. Here's my internal stress. Now I'm going to go from B to C. Shear stress from B to C is torque from B to C, which is C from B to C, which is J from B to C. And I had negative 175 pound-feet, 12 inches per foot. That outside radius, 0.75 inches, divided by pi over 2, 0.75 to the fourth. Sorry, I'm trying to process another video while I do this. Okay, so when I multiply this out, I get 175, and it's negative. I need to keep that in mind. It was negative 12 times 0.75 times pi as a number, 2 divided by 0.75 to the fourth, and I get negative 3169 pound per inch squared. Okay, negative 3169 pound per inch squared. Now I need to go from C to D. From C to D equals the torque from C to D, the C from C to D, the J from C to D, and I'm going to get an internal, it's still that negative 175 pound-feet, still times 12 inches to make our units, but this time I have an outer radius of 1.5 inches, and then my my J is 1 over 2, outer 1.5 to the fourth minus inner. And when I multiply this out, I get 175 negative 12 times 1.5 times pi as a number 2 divided by 1.5 to the fourth, 1.5 to the fourth minus times divided by. I get negative 1348 pound per inch squared. Okay, and why is that such a different number? Even though they have the same torque, they both have the same negative 175, but they have different cross-sectional properties. So it's a function of that internal torque, but it's also a function of internal properties. So this is at minus 1348. And then I do the same thing from D to E. Shear stress from D to E equals torque from D to E, C from D to E, J from D to E. And I can go back to my torque diagram. I have 650 pound-feet times 12 inches per foot times that outer radius was 1.5 pi over 2, 1.5 to the fourth minus 1.375 to the fourth equals 650, 12 times 1.5 times pi. So number 2 divided by 1.5 to the fourth, 1.375 to the fourth minus times divided by. And I get 5,005 pound per inch squared. Okay, I'm going to recheck that math. 650, 12 times 1.5 times pi as a number 2 divided by 1.5 to the fourth, 1.375 to the fourth minus times divided by. Okay, so that's my stress. So I can come back over here, and I'm way up here now, way up here to 5,005. So where is my maximum stress? I have a 1720, a minus 3169, a minus 1348, and a giant whopping number up here. I'm trying to refocus, but I can't find my little mouse. Okay, so this would be my maximum internal stress. So max for my system is 5,005 pound per inch squared. Okay, I'm going to make a second part of this video to go back and do rotational